probably the hardest thing about the Taylor series and Maclaurin series is finding them. So what we want to do is take an example and go through a process of how we would find a Taylor series for a function. Okay, so in this case we're going to do a Maclaurin series, but we could do a Taylor series at any arbitrary center. But let's start with a simple example where the center is equal to 0. Because ultimately the key, we're looking for patterns. Every time you do this, you're looking for patterns. And so what that means is you may have to generate, you may find the pattern in 2 terms, but a lot of times it's like 4, 5, 6, 7. And until you get really good at this sort of pattern finding, it can be difficult. So you just know that you might be in for a little bit of work. So anyway, let's say we're trying to find natural log of x plus 1. We're saying I want to find the Maclaurin series for this. And so ultimately I want to get something that matches this type. You know, the nth derivative at the center over n factorial times x minus c to the n. Now remember, for Maclaurin series, c is 0, so that's the nth derivative evaluated at 0, and the center is 0, so this just becomes x to the n. So we take our function, we take its first derivative, which is 1 over x plus 1, and then we take the next derivative, we do the power rule, we bring the negative down, it becomes x plus 1 to the negative 2, keep going, you bring the negative down, you now have 2 to the negative 3, you do it again, negative 2, so that negative comes down, so it's 2 times 3 to the negative 4, you bring that down, the negatives cancel, so you end up with 2, 3, 4, x plus 1 to the negative 5. And you might ask yourself, why in the world am I not just multiplying all these together? And the reason I'm not doing that is because a lot of times it can be very useful to leave them in that sort of chained mode, because you might notice a pattern by leaving them in that chained multiplication that would be difficult to see if you lumped them all together. So the reason I say that is because let's evaluate this thing at x equals 0. Well, that becomes a natural log of 1. Natural log of 1 is 0. When x is 0 here, it's just 1 over 1. So that's 1 there. In this case, it's also 1 squared in the bottom with a negative, so negative 1. This is 1 cubed with a 2. So what you're seeing here is each time this x plus 1 sort of disappears because it's just 1 to a power. So you end up with a 0, 1, negative 1, 2, negative 2 times 3, positive 2 times 3 times 4. Notice that I included the 1s here as well, because I'm trying to pull out a pattern. Well, let's look at this. Okay, I've got these. What are some of the things that I notice? Well, I notice that the 0th term is 0, so that starting 0th derivative is 0. So that's going to tell me a little bit about where my index starts, but we'll get back to that. Now, I also notice that it's negative when the when n is not odd, when n is even. Sorry, that should be n is even. Alright, so for the 0th term, this would be negative, but it's actually just 0, so negative 0 doesn't matter. Negative, negative. If you kept going again, you'll see it's negative, because each time it's just going to swap, so you'd have negative, negative, negative. And the coefficient for the nth term, this coefficient here kind of looks like a factorial, right? I have 1, 1, 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4. But the factorial doesn't match this number. It looks like it's 1 less. So it's not 5 factorial, it's 4 factorial, 3 factorial, 2 factorial, 1 factorial, 0 factorial. So it looks like it's not n factorial, it's n minus 1 factorial. So that tells me that my guess for that nth coefficient is negative 1 to the n plus 1. So that means if n is even, this thing will be negative, but if n is odd, this exponent becomes even and the negative 1 disappears. So it's just like a light switch turning on and off. And then I have n minus 1 factorial. So that tells me what this term is, but I really need it to be divided by n factorial, so I do that. Now when I plug that in, I have n minus 1 here when I had n plus 1 here. They're really the same thing because they would have the same behavior, so I apologize for that. but I have n minus 1 factorial over n factorial. Well, we know that n factorial splits into n times n minus 1 factorial. So the factorial pieces cancel, so I get negative 1 to the n minus 1 over n, which tells me that my power series for natural log of x plus 1 is that coefficient, negative 1 to the n plus 1 over n times x to the n. So there you have a power series for natural log. Great, I did a lot of work, I got a natural log power series. What's cool about this is that we can use this to generate a power series for other functions. I might ask, okay, well what's the series for 1 over 1 plus x? What does that look like? Well, I know that 1 over 1 plus x is the derivative of the natural log, right? I know it directly from here. So if I know that's true, now instead of taking the derivative of, or instead of just generating a power series, which I could do, and I could also use a little bit about the geometric power series to kind of cheat and get this one. But I know the power series for the natural log, sorry, should be x plus 1. A lot of mistakes in this video, I apologize for that. Well, the derivative, then I can take the derivative of a polynomial, right? The derivative of a polynomial, the n comes down with the power rule and those would cancel. So now I just have this term, an x to the n minus 1. So n equals 1 to infinity. Now I can re-index this series. You don't have to. You're welcome to leave it like this. But a lot of people would re-index it so that n starts at 0. And then the reason why they do that is because you can combine those into negative x to the n, and then it looks a lot more like that geometric series, that geometric power series. So it's easy to verify that we've done this correctly. But what's nice about this is I could say, okay, well, if I wanted that 1 over 1 plus x squared, I could continue to use this power series to generate that. So it makes it easy to generate power series for all the derivatives of a function just by taking the derivative of the parent power series, and you get into with a polynomial expression, which is super nice because polynomials are way easier to deal with than pretty much anything else.